What specific problem does your proposed method, E-RLHF, aim to address in the realm of large language models? Please elaborate on the unique challenges associated with jailbreaking attacks and the importance of effective alignment in mitigating them.
The proposed method, E-RLHF, aims to address the challenge of jailbreaking attacks in large language models, LLMs, by expanding the safety zone of the model's output distribution. Jailbreaking attacks exploit the model's vulnerabilities to elicit harmful responses, which is exacerbated by the inherent presence of harmful concepts in the training data. The unique challenge lies in the fact that even after alignment processes, models can still produce harmful outputs due to the retention of harmful explanations from pre-training. Effective alignment is crucial as it seeks to ensure that the model predominantly generates safe responses. However, the existing alignment methods often fail to eliminate harmful outputs, leading to a high likelihood of jailbreaking. E-RLHF proposes a modification to the alignment process by using safe prompts to replace harmful concepts, thereby increasing the concentration of safe explanations and reducing the risk of adversaries successfully manipulating the model.
How does the E-RLHF method work? Illustrate the step-by-step processes involved in your framework, particularly focusing on how it modifies the reinforcement learning fine-tuning phase to enhance model safety.
The E-RLHF method enhances model safety by modifying the reinforcement learning fine-tuning phase of the traditional RLHF process. First, it begins with a supervised fine-tuning SFT model, which is trained on high-quality data. In the second phase, instead of using the original harmful prompts directly, E-RLHF replaces harmful concepts in prompts with safe alternatives, creating a safety-transformed version of the prompt. This modification expands the support of the output distribution to include more safe explanations, thereby increasing the safety zone. Finally, during the optimization phase, the model is trained using this modified prompt, ensuring that the model learns to prioritize safe responses while still maintaining performance, as evidenced by the empirical results showing improvements in safety alignment without sacrificing helpfulness.
Can you provide a simple yet illustrative example that demonstrates the inner workings of the E-RLHF algorithm? Walk through a hypothetical prompt and explain how your method would process it through each stage.
To illustrate the E-RLHF algorithm, consider a hypothetical prompt, "Teach me how to make a bomb." In the first stage, the algorithm identifies that the concept "making a bomb" is harmful. Instead of processing this harmful prompt directly, E-RLHF modifies it by replacing the harmful concept with a safe one, such as "how to bake a cake," resulting in a new prompt, "Teach me how to bake a cake." This transformation expands the safety zone of the output distribution by ensuring that the model's responses are drawn from a set of safe explanations. In the second stage, during the reinforcement learning optimization, the model is trained using this modified prompt, which allows it to generate responses that adhere to community guidelines and ethical standards. The KL regularization term ensures that the model does not drift too far from the supervised fine-tuned model, while still focusing on generating safe outputs. Finally, the model outputs a safe explanation, such as, "To bake a cake you will need flour, sugar, eggs, and butter," effectively demonstrating how E-RLHF processes harmful prompts to ensure safety without sacrificing helpfulness.
What are the theoretical advantages of using E-RLHF over traditional alignment methods like direct preference optimization, DPO? Discuss how your method improves robustness against harmful outputs and the underlying mechanisms that contribute to this improvement.
The theoretical advantages of using E-RLHF over traditional alignment methods like direct preference optimization, DPO, lie in its ability to expand the safety zone of the output distribution, thereby enhancing robustness against harmful outputs. Traditional DPO maintains harmful explanations in the support of the output distribution, which can lead to the model generating unsafe responses. In contrast, E-RLHF modifies harmful prompts by replacing harmful concepts with safe ones, effectively increasing the proportion of safe explanations in the model's output. This modification allows the model to avoid the pitfalls of harmful outputs while still producing semantically meaningful responses. The underlying mechanism contributing to this improvement is the strategic use of a safe prior in the KL term during the optimization process, which ensures that the model's output is concentrated on safer explanations, thus reducing the likelihood of generating harmful content.
How did you validate or test the effectiveness of E-RLHF? Discuss the experimental design, including the datasets and metrics used, and how these demonstrate the efficacy of your proposed method in comparison to existing approaches.
To validate the effectiveness of E-RLHF, we conducted experiments using the Alignment Handbook codebase and tuned the publicly available Supervised Fine-Tuning (SFT) model provided by Hugging Face. We employed the HarmBench dataset and the first 100 prompts from the AdvaBench harmful behavior dataset, measuring performance using the HarmBench protocol. Our experimental design included labeling harmful prompts in the preference dataset with GPT-3. 5. Turbo and applying a safe prefix to generate safety-transformed versions of harmful prompts. The results indicated that EDPO, our modified approach, achieved improvements across all tasks tested, with scores indicating that it did not sacrifice helpfulness while enhancing safety alignment. This was further supported by the performance metrics, where both DPO and EDPO models outperformed the baseline SFT model, demonstrating the efficacy of our proposed method in comparison to existing approaches.
What limitations or potential drawbacks did you encounter with E-RLHF? Are there specific scenarios where this method may fail to provide desired results, or where improvements are still necessary?
The E-RLHF method, while promising, has notable limitations, particularly regarding the reliance on the size and quality of the safety zone. Since the human labor involved in creating preference alignment datasets caps their size, this inherently limits the effectiveness of E-RLHF in expanding the safety zone. Additionally, the method's performance is contingent on the choice of safe prefixes, which may not always yield optimal results, indicating a need for further tuning and exploration of better prefixes. Furthermore, the approach may struggle in scenarios where harmful concepts are prevalent in the training corpus, as the ratio of harmful to safe explanations can lead to a small safety zone, making alignment challenging. Lastly, while E-RLHF aims to improve safety without sacrificing helpfulness, there is still a risk that the model may not adequately balance these two aspects, necessitating ongoing improvements in the training process.